This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Felienne for Software Engineering Radio, and I'm here today with Moshe Vardi. He's a professor of computer science at Rice University and also the director of the Ken Kennedy Institute for Information Technology. His interests focus on applications of logic to computer science, including databases, multi-agent systems, verification and reasoning, and on how to teach logic across the curriculum. Welcome to the show, Moshe.
Thank you, it's good to be here.
I just listened to a great keynote you gave at ICSE, the International Conference on Software Engineering, and I'm going to ask you a few questions today about what we covered this morning in the keynote.
Please do.
The first thing that you talked about this morning was this intriguing problem we have in computer science called P versus NP. I heard it's such an important open question that if you can solve it, you get $1 million. So that seems really exciting. How do I get those $1 million? Can you explain to me what exactly P versus NP means?
P versus NP is a question in theoretical computer science. It's now also accepted to be a major open problem in mathematics. And the basic intuition there is actually very, very simple. If you think through when you were in high school and you have to solve maybe linear equations, and you had to learn how to solve linear equations, and you came up with a solution, and the teacher would look at your solution and very clearly would tell you correct, not correct, without solving the problem herself. And how did the teacher do it? All the teacher had to do is to plug your answers into the equations and see whether it works out or not. So this is checking solution. So finding solution seemed to us intuitively harder than checking solutions. And in fact, there are many, many, many problems where it's fairly easy to check solutions. In fact, our very language assumes that finding solution is hard, but checking is easy. When we talk finding a needle in a haystack, nobody talks about checking that the needle is indeed there. It's obvious that if once somebody points at the needle, you can check that it's there. And so we have this intuition that solving problem is difficult, but checking should be typically easier. And we have many, many, many problems we can formally show we can check solutions efficiently. And these problems are called NP. The acronym itself has a history, let's ignore it. But it's called NP. NP problem that solution can be checked efficiently. Now there are fewer problems where we know how to solve them efficiently. So linear equations is an interesting example because we know how to solve them efficiently. You were taught an algorithm in high school called Gaussian elimination, and that's an algorithm that enables you to solve efficiently linear equations. But there are many problems where we do not have yet efficient algorithm. For example, the problem of Hamiltonian cycle. Given a graph, a network, which is a set of nodes and a set of edges between them, you can think of transportation network or the call graph of a large program. These are all defined networks. And the question is, does a given network have a Hamiltonian cycle? We don't know how to do that efficiently. It's a major, major open problem. On the other hand, if somebody gives you a candidate solution, I think this is a Hamiltonian cycle, you can check, because what are the rules? It has to be a cycle, which means it has to start and finish at the same node. Each transition has to be over an existing edge in the graph, and you cannot visit every node more than once. These are all easy to check. So we can check solutions efficiently. Can we find solution? Can we solve the problem efficiently? We don't know that. And this is the question what NP versus NP is about, is ask checking versus solving. Our intuition says that checking is easier than solving. We have no formal proof of that. And it's conceivable that we are wrong. The intuition is misleading us. Maybe there is a magical way to turn every checking algorithm somehow into a solving algorithm.
So are we getting close?
Not really. There is a German phrase, and maybe there's a similar Dutch phrase, and Mensch planen, Gott lachen. Man plans and God laughs. This problem is laughing at us. It's now open since the early 70s, so we are now about 74, 71, I think, so 46 We're going to celebrate in a few years the 50th anniversary of the problem. We are not one bit closer to its solutions than we were 50 years ago.
However, you mentioned this morning that there's also some good news, because it's not hard to solve P versus NP in the sense that we only need one solution to eradicate the question once and for all. So can you explain how that works? Why do we need to only solve one?
So one of the things that we have, it's unfair to say we're not closer. The terrain is understood much better. We don't know whether really we're up to a solution, but we have a much deeper understanding of we have a whole theory, it's called computational complexity theory. And the fundamental concepts are now very, very clear to us in a way that they were not, and you have to remember, but in the 50s and the 60s, people tried to address this problem that seemingly on the face of it, the only way to solve them require exhaustive search. The only way we just to keep trying different cycles in a graph until we find a Hamiltonian cycle. And there were, for 20 years, 56, no progress was made. And the big progress in the early 70s was one in this elucidation between checking and solving. That's one thing. And the secondly is we can understand that certain problems are called NP complete. And what that means that in this class NP, the class of problems that can be checked in polynomial time, which means efficiently, these are the hardest problem. And Hamiltonian cycle is such a problem. And the traveling salesman is also such a problem. And what we know about all these problems, that in some sense they are equivalent to each other. If you can solve one, you can solve the other one. If a single one. By now we have thousands of such problems. In fact, we have lost count. The early years, people would count, there was a taxonomy, and then by the 80s, people said, well, it's just like a zoo. We can't keep track of it anymore. So we don't know how many problems. But the estimate is thousands of NP-complete problems. In fact, this theory was developed in the early 70s. By the time I was a PhD student around 1980, and I tried to submit a paper saying that a certain problem is NP-complete, and it was rejected. This is not publishable anymore.
It's boring. Everyone,
it's kind of,
we have enough.
Yeah, not publishable anymore. I was disappointed, but this is life. But all these problems are NP-complete, and one of them is Boolean satisfiability, which we'll get to in a few minutes. All of them are formally equivalent in the sense we can solve one efficiently, we can solve every other problem efficiently. And that means that in principle, if you resolve one of them, we showed that one of them is in polynomial time, can be solved efficiently, all of them can be solved efficiently. And so people usually focus on some problems seem to be more attractive than others. For example, Hamiltonian cycles seem to be a very popular problem, and people have published in quotes alleged polynomial time algorithms for this. All of them were wrong. But if somebody is interested, they can go and Google and they can find a nice websites that summarize all the proofs that have been published so far, all wrong so far, that P is equal to NP, and all the proofs have published so far that P is different than NP.
Okay, we'll make sure that that's in the show notes. We have a list of links we can include, so we will make sure you can read all the proofs after the podcast if you want to.
In 2010, and an HP researcher by the name of Deo Lalikar announced a big proof that P is different than NP. And the paper looks serious. It's formatted in LaTeX, so it must be serious. Not like, in technical paper, it's formatted in Word, we are suspecting immediately, but LaTeX, so it looks credible. He was a principal researcher at HP Lab, so there was the veneer of respectability. So people took it seriously. I was very excited. So he claimed that he has a proof that P is different than NP. And he was using a theorem that I proved many years ago when I was a postdoc. And so I was excited. Maybe my theorem will be used to prove this. But the proof collapsed within about, he had his, not 15 minutes of fame, but 15 days of fame before the proof completely collapsed.
Because someone found a flaw in it.
There was a big flaw in it. There was
That's
a major flaw. So the problem attracts lots of attention. Recently, a few years ago, somebody said the solution would lie in algebraic geometry, a very deep mathematical field that most of us know nothing about. Most of us don't plan to study it. So far, nothing has happened. And there were various attempts over the years. People come up with, this is a promising direction, and here's a promising direction. And each time there's a promising direction, For a few years, there is some excitement. Everybody's trying this promising direction before they realize it's a mirage. We're not making progress.
And even though there's no proof, most people assume that P is not equal to NP. What would happen if P turned out to be equal to NP?
So I have to say that while this is a prevailing wisdom, I declare myself as an agnostic. First of all, I said I don't have this deep conviction that other people have.
Okay.
While some other people, like Don Knuth, Donald Knuth. I mean, who can? This is probably maybe the greatest computer scientist alive, or one of the few greatest. There are few people in this caliber, and he is on record. He believes that P equal NP. And one reason also is because one of the things that we have discovered in the 80s, that certain problem can be proven to be solved efficiently without demonstrating the algorithm.
Oh.
So typically we think that if I want to show you that a certain problem can be solved efficiently, I have to show you an efficient algorithm. But people show that there's a certain proof technique that shows a certain problem that an algorithm exists without actually exhibiting the algorithm. And so that means that we might even be able to show that P equal NP, and it will give us nothing.
That would be so frustrating.
It would be immensely frustrating. All we will have is there exists an abstract proof that an algorithm exists. We will not be able to lay our little dirty hands.
All of us are too stupid to figure out what it is.
Yeah.
So one thing we already talked about that a little bit is SOT solving. This is one of those problems that is NP complete. Why is this such a special problem? Why are people focusing on this one?
So one is history. The history is that it's in some sense it's almost the beginning of. So logic is a very old field. It goes back to Aristotle and then the medieval logic. I mean, there's a long history. But in the middle of the 19th century, George Boole formalizes it. We have now Boolean algebras. And so now it's suddenly moved from philosophy to mathematical logic. And in the middle of the 19th century, people realize it is such a simple problem. It's just reasoning about true and false.
Yeah, because maybe it's a good idea for our listeners to explain first what exactly Boolean satisfiability is.
So Boolean logic is a very simple logic. It's a logic of true and false. This is it. Two truth values, nothing more. Everything is true or false. And then we can combine things. We know that not true is false and not false is true. We know that true and true is true, but true and false is false. We know that true or false is true, but false or false is false. These are very simple rules.
And these are things people use in programming
We
every
use them.
day.
We use
It's
in programming.
very
You
natural
write
thing.
condition. We use this thing all the time. We use the and the or and the not all the time. You cannot think of any conditions if you don't have the ability to combine. And these are the basic combine. In fact, we know that you don't need any more than and, or, and not to create any Boolean function. Not to mention the people who build hardware, every logical circuit
Is Boolean logic.
Is Boolean logic. In fact, when we talked about, when electrical engineering talk about logic, it's Boolean logic they have in mind. So it's incredibly fundamental logic, and we would like to reason about it. And one simple question: if you're giving the problem in a symbolic way, that is, you have variables that stand for 0 or 1, true or false, and they are combined using and, or, and not. The question is there a way for this expression to form 1? You can think of it in a very simple way. When you write a conditional, your intention is that we should be able to, there should be both outcomes. There should be a true outcome and a false outcome. It's if, then, else. You think that both outcomes are possible. But if you write a very complex expression, maybe it's not. It's possible that you wrote an expression, for example, maybe what you wrote is something complex, but it's really equivalent to x equal 1 or not x equal 1. And then it's always going to be true. Or maybe you wrote something that, again, it's complicated, so you don't see it, but if you simplified it, at the end of the day, it's equivalent to
A and not A.
A and not A. And so you'll never take that branch. So kind of one of the basic sanity we have about programs, we want to make sure that every branch can be taken both ways. So this seems to be a very, very simple problem.
Yes.
Turns out that the only way really we have how to solve it, in principle, is by trying all combinations. So this is okay if I have two variables, P and Q, then there are 4 possibilities.
You can make a truth table. That's what you would
Truth
do.
table. But if there are, what happens if there are 10 variables? Well, but now there are 10 to the 10, 2 to the 10, it's 1,000 possibilities. Okay, maybe it's doable. Or if not, I can write a program to do it. But what happens if I have 50 variables? Now, as it turns out, you can argue that people very rarely write in software this combination of things. But now, let's think about, I want to know whether a particular path in a program can be taken, okay? So there is a program and there are many paths that I can execute. And then I want to know, for example, I would like to come up with inputs that cover all the possible branching of the program. Now, if you look across a branch, it will have many, many conditions along the way. And by the time, if it's a long branch, you may have hundreds of variables in that particular branch. Now you say, wow, 100. Now I have to check 2 to the 100 possibilities. It's a very large number. 2 to the 100 is about 10 to the 30, so it's about, what is it, about 1,000 trillion. It's not going to work.
And this is one of those NP-complete problems for which we don't have an efficient solution, but it's easy to check. Because if you give me an assignment for all the variables, I plug it in,
and I know, remember, they're a very simple rule, right? True and false is false,
exactly.
True or false is true, not true is false. So it's very easy to evaluate it. It's very easy to check if you give me an assignment. But on the face of it, finding an assignment seems to require exhaustive search. We don't have anything better than in principle. And we'll talk a little bit about refine this in principle in a few minutes, but in principle, seem to take exhaustive search. So this problem is of immense importance in the basic in software. You write software, there are many, many questions about software can be reduced to Boolean reasoning.
Can you give a few examples?
So and I said the simplest example is you want to generate data. So one way, even if you want to do a test suite, and you want to make sure that you have good coverage, you want to have branch coverage. So that means that you are trying to make sure that you have data that drive you into every branch of the program, and then else, the two options. And so how do you generate such data? So one way to generate such data is to do symbolic execution along different paths. And each time you do symbolic execution, you're getting expression that you accumulate along the different assignments and in the branches, and then you give these expressions to a constraint solver, to a SAT solver, and the SAT solver will give you solution, and solution is guaranteed to take you to that particular location.
But wait, how can a SAT solver do that? Because you just told me the only way we can do this is by checking all possibilities.
So the amazing development, in particular of the last 20 years, is this growing gap between the seeming difficulty of the problem from the theoretical point of view. It's an NP-complete problem. Many of us were educated to think NP-complete means scary, unsolvable, there's nothing we can do, give up, just lie on your back and whimper. But the reality of in particular, this actually the history goes back to the early 60s. People have been thinking about it very hard for a long time. We have to remember, in the 19th century, people says, this is a very, very important problem. Ernst Schroeder, a German mathematician, said, this is the ultimate problem in mathematics and logic.
Wow.
This is very important.
And this was before there were computers?
They were doing computation by hand.
On paper.
But they wanted something fast, and they couldn't find anything fast. And people have been looking at it now in computer science, going back to the first program was written to do it was 55. So we have now over 60 years of doing it. And I would say from these 60 years, the first 30, 35 years were very, very slow. I mean, when I was a young researcher, there was a small group of people who did that, and many other people almost looked at them in disdain because they were making incredibly slow progress. They were able to solve hundreds of variables, which is not trivial, but still it's way too small for many practical problems. And the progress was incredibly slow. And people thought, why waste your time? It's NP complete. How much progress do you hope to make?
Was there at one point one big breakthrough?
There was a sequence of breakthrough. I would say, in particular, there were a few key ideas that were developed roughly around between mid 90s, 96 to 2001 seemed to be kind of a magical period. Some of these ideas that existed before, and people have repurposed them. For example, there is an idea of what's called back jumping. Back jumping means, so all of these approaches today are pretty much, all the successful general approaches are based on backtracking search. You take the expression you're trying to solve, a formula we call it also, and you choose a variable and you assign to it 0 or 1, and you simplify and you continue to make assignment, and if you're lucky you find a solution, and if not you realize I failed and you backtrack. So this is essentially backtracking search.
Yeah.
So
something simply, it's still trying all possibilities.
Essentially, we know that backtracking search in principle is trying all possibilities. And we know that the worst case complexity is going to be, you're going to try all possibilities, it's going to be exponential in number of variables. And backtracking search is a very basic technique that we teach all students, usually in the first or second year, right? It's how we solve many, many problems. And we know that it doesn't scale if you have large number of variables. What people discover is that you can start to accumulate new ideas. For example, one idea was back jumping. Back jumping meant that when you backtrack, means that you made an assignment and you failed. Don't act reflexively. Spend some time analyzing the failure, because it might be that you realize that the reason for the failure is some assignment you've made a bit higher up.
In the tree.
So jump back to the arrow. Okay, jump back to the source of the problem. So one of the things I said in my keynote, many of the ideas, many of the heuristics in solving are heuristics for life. Okay? So for example, you made a mistake, analyze your mistake and learn from your mistakes. And so backjumping is one example. But even more importantly, and this is in 1996, researchers in the University of Michigan realized that when you make a mistake, even though you may have assigned hundreds of variables, it could very well be that the reason for the mistake is some small fraction of this. Maybe only 5 variable assignment, that's really the reason for the failure. And so you said, this particular assignment to this 5 variable, I should not do it again. So you write yourself, don't make this mistake again. It turns out that you can write in a logical formula, don't make this particular mistake again. So you write a new, we call it a clause. It's a disjunction, is to say, do not assign x1 to true and x3 to false and x5 to true. And this you edit as a new requirement. This is now a new constraint. So not only you have learned from your mistake, but you write it in the same syntax of the formula itself. So now it becomes part of your formula. So you have changed the formula. Now you have the formula plus all the mistakes that you should not repeat. And in fact, on big formulas, this becomes known as conflict-driven close learning. So the conflict, it means a bad assignment. An assignment is in conflict with the formula. And the clause is this forbidden partial assignment. We call it a clause. So CDCL is the new way we describe this kind of such solvers. Because the such solvers they're learning. Every time they make a mistake, they say, I made a mistake. What went wrong? Let me understand what went wrong. And there is a whole data structure now that supports, we follow what the assignments are doing, and we can go back and analyze it. We have something called an implication graph, and it learns about dependence between these variables.
Yeah, so if A is true, then we see that always B also has to
must
be true.
And so we draw this graph, and that means now that if the problem was these assignments of A and B, but A implies B, we don't care about B. It's enough that we remember that we should never make A true, because if A is true, then B is true. And so CDCL is the new vocabulary, the new term that we have for such solvers. And so these solvers now are not only pure solvers, pure search solvers, because when they learning is inference. They make new inference. They look at the original set of conditions and they generate new conditions.
And do they typically do that while they're solving? Or is there also a process where the SAT solver could look at all the clauses and do some inference before even starting to assign variables?
So there is a whole bunch of other things that people have discovered. For example, they call it preprocessing. When you get a formula, don't rush. First of all, see what kind of low computational effort you can do to massage your formula in advance. For example, let's suppose that a particular variable appears only once. Only once. Somewhere we see suddenly something that says P. That's it, only once. So wait a minute. If I decide that this is, if by making it true, I don't ruin anything, there's no other reason anywhere that would say I should not make it true. Things are complex usually because sometimes P appears positively, but sometimes it appears negatively. P and somewhere else not P. But if P appears only positively,
you can just make it true.
I just make it true, and I'm done. So this is an example of very low cost assignment. In fact, when I do this, the formula would simplify. So very often we can do a lot of pre-processing to make the formulas simpler. So people started with this closed learning. There was a big, huge breakthrough that came from Michigan. And then a few years later, another breakthrough. Somebody said, what is my SAT solver doing? And decided to profile it, to see where does the code spend its time. And discovered that 80% of the time, the code was spent manipulating a certain bookkeeping operation that looked completely trivial. It was considered to be a completely standard, non-controversial bookkeeping operation. And then they discovered to their surprise that 80% of the time was just managing this bookkeeping, updating counters. And say, wait a minute, this is not supposed to be a computationally heavy thing. So it turned out that there was some counter that had to be kept, but they have to be updated all the time. And so it was consuming enormous amount of effort.
The counter of what? Can you explain
So
that?
the counter is what happened is, remember, we have constraints. And the constraints, when you convert one of the pre-processing we do, we'd like to simplify the syntax of the initial formula.
Okay.
Instead of having some completely crazy formula, we have ways to reduce it to so-called conjunctive normal form. Conjunctive normal form means it's a conjunction. Conjunction is and of disjunctions, of ors, of variables that are either appear positively or negatively. Conjunction of disjunctions. Now, what happens if one of the disjunctions has, usually it would be P or Q or not R. What happens if one of these junctions is what we call a degenerate disjunction? It's a unit clause. It's a special case of a disjunction, contains only a single variable. Because it appears in a conjunction, everything in a conjunction must be true. So once a particular disjunction shrinks to a single variable, positive or negative, that variable tells us P must be true or P must be false. And now we don't have to make a choice anymore. There's no more, this choice has been forced on us.
Yeah.
The choice has been made for us. Therefore, and when the choice has been made, you immediately say, okay, we'll make this variable true. When you make it true, you go wherever it appears and you simplify. Now you plug in, you do constraint propagation. You plug the values and you simplify the expression. As you do that, other clauses may become degenerate clauses. And you do it again. And this is something that doesn't require no backtracking on this one. So you can do it very, very fast, but you have to keep track in every clause, in every disjunction, how many variables I have.
Because it only works if it's just the one.
It only works when it's one. So you basically start by having, okay, you have 10 and 9, and then you come down to 1, you say, jump on it, do it.
We're ready.
I'm ready for it. Now what happened if I do all this, it's called BCP, Boolean constraint propagation, and then I have not been able to simplify the formula completely. Now I have to go back to making choices and continue the backtracking search. And what happens if this particular search failed? I have to backtrack. When I have to backtrack, I also have to undo all these propagations.
All the results.
And in particular, I have to go and update all the counters. So before that, I decremented the counters, and now I have to go back and increment the counters because this was a wrong choice. And it turned out that just incrementing and decrementing the counters or consuming 80% of their runtime. And they did something that people have not done before. They just profile the damn code.
This podcast is supported by Atlantic.net, hosting solution provider of healthcare HIPAA, PCI compliance, and ad tech. If you're feeling the pain of having outdated technology, call Atlantic.net and get the latest security firewall, intrusion detection, backup, disaster recovery, and virtualization. Or if you're starting a new project or not getting the results you want from your current providers, Atlantic.net can help you succeed. With fully audited solutions and 23 years in business, they won't let you down. Visit Atlantic.net to learn more.
It's so cool. It's an NP-hard problem, and then let's just do some profiling and you find something.
And so this is, wow, we have to have a better way of doing this. And in particular, they wanted to get rid of it's one thing to decrement the counter, but because you backtrack a lot, you don't want to do it when you go back, when you backtrack. You don't want to increment the counters back. And they came up with a very ingenious data structure that it will be hard to explain just on the radio. But the data structure was such, it required an update when we assign variables, but we never have to update it when we unassign a variable, when we backtrack. So it saves a lot of time. This is called, it has a name, it's called two literal watching, just keeping two pointers, and we won't go into the details. But that, again, was a very simple idea. And these two ideas by themselves, that close learning and two literal watching, suddenly the stat solver starts solving bigger problem. And so by 2001, people realized, wow, something is happening here. This is not the old stat solvers. And then they start looking at other heuristics that can come into the picture. Okay, so bed jumping was a heuristic that existed before. People in consent solving came up with it. People said, let's use it here. Very useful. Another heuristic that came up from Princeton was you have to choose variables to assign 0 or 1. As you do the backtracking search, each time you have to say, okay, what's my next variable?
Which one shall I pick?
Which one shall I pick? And people have over the years thought of more and more sophisticated heuristic. It's called also a decision heuristic. Decide which variable to assign. And people have come up with more and more sophisticated heuristic. Why? Because they thought that the goal would be to have a smaller search tree, to have as little backtracking as possible. People say backtracking is bad. Let's try to minimize backtracking. And the problem was they would not realize you're spending more and more time making a decision. So while your search tree was smaller, every node in the search tree was consuming more and more time. And again, the Princeton team says, let's relax it a little bit. Let's focus on a decision heuristic that is not too stupid, but equally important, is very fast. And they came up with a very good heuristic, strike a balance between how smart it is and how fast it is. And so when we look today, when we compare the search trees of the new heuristic to the old heuristic, the search trees are bigger, but we spend so much less time at every node
that you have time left to just try
overall we save time.
Yeah.
So the key thing that they observe is that the time that you spend is the size of the tree, the time that you spend at every node. And even though one is becoming bigger, if the other one is small enough, you still gain.
And can you give an estimate of how much speed up we've acquired in all those years? How much quicker have they become?
So to answer that question, a colleague of mine at Berkeley decided a few years ago to benchmark 12 years of stat solvers. So he took 12 years of stat solvers from 2000 to 2012, and he applied them to the same benchmark. Over the years, they were all published in different papers. They were run on different machines or different benchmarks. He said, I'm going to take one 2012 machine, one benchmark, and compare 12 years of such solvers. And he showed that the problem was taking 800 seconds in 2000. So remember, 2000 is before the 2001 breakthrough at Princeton, but after the 1996 breakthrough in Michigan. What was taking 800 seconds in 2000 was taking 1 second at 2012. So this is 3 orders of magnitude improvement. So we went from 800 seconds over to 1 second, which is really roughly 3 orders of magnitude in 12 years. That's just an astounding progress. Now, somebody needs to redo it now to see what it will be now after, instead of just 12 years, 17 years, and do the comparison. But there is an annual competition, so we kind of see that we are still improving in a double-digit speed every year. And nobody quite understand why are we making such good progress, except that lots of human ingenuity is going into it. And everybody has a goal now to go and submit another entry to the SAT competition and become the champion. It's a very good motivator. And people talk about Moore's law for SAT solvers kind of as a half joke, because we seem to just constantly making a progress every year. So it's not 60% per year. We're not quite where Moore's law was, but we're still making double-digit improvement per year.
So if we come back to P is MP, maybe it doesn't really matter all that much whether or not it's the same, because we make so much progress that after a while we can solve the MP problems really quickly, even though it's not polynomial?
So we have to be careful. So the answer to your question is yes and no.
Okay.
So we know that SAT is a difficult problem, because once you understand how good solvers work, you can generate artificial hard instances. So we can today generate instances with a few hundred variables that no one can solve. We know how to do that. But these are all artificial problems. There is something magical about problems that come from industrial problems. From, for example, this, as I told you, these tools that Microsoft is using, which is to do symbolic execution along execution path, collect the conditions, solve them, and then get inputs that will drive the program to a particular desired location. Or people using more sophisticated technique. Model checking is a technique of doing kind of very heavy-duty static analysis of program to understand, for example, I may want to know in bounded model checking, I want to check that all paths of a certain length will never reach do an assert violation. Okay, so maybe when I can do it, there's even some technique how I can do it for arbitrary length path. But all these techniques are very, at the end of the day, they use SAT solvers as their underlying engines, and this problem somehow to be much, much easier than these artificial instances we know how to generate. So it's not as if NP problems suddenly have become easy. There's something about, and not all of them. We run once in a while, we run the problem, we say this one we cannot solve. But a very, very large number of problems that come up from industrial applications do not seem that difficult. And what do I mean by that? We today are able to solve problems, SAT problems, with up to 5 million variables. This is astounding. Remember that about 25 years ago, we were dealing with 500 variables. And in this 25 years, we went from 500 variables to 5 million variables.
5 million. So the possible number of options is 2 to the power of 5 million.
That's a number that does not exist in the universe. Okay? And of course, we are not covering such a space. Of course, the whole point is that we reduce it dramatically using all these heuristics. We reduce it very, very dramatically.
Wow. So let's talk a little bit more about applications. We've already talked about the Microsoft work. Can you talk a little bit more about that? They have their own solver, don't they?
So Microsoft has been really at the forefront. One is they have people in Microsoft Research that have worked to develop some of the best SAT solver. They have a tool called Z3. And this tool, I believe, is actually available.
Yes.
And you can use it. Other people can use it.
We will link to it in the show notes.
And they have a whole suite of tools. And again, many of these tools are available. I don't know about each specific tool, but many of the tools are available. One of the tools that was developed even before that, but became much better, was the development of SAT solver. Is a tool, I think it's called SDV, Static Device Verifier. And this is a tool to make sure the device drivers are complying with the protocol of the operating system. So it turns out that many of the time when you get a fatal failure, you get like a blue screen, it's really as a result of mismatch between the device driver and the protocol of the operating system. And so people were blaming Microsoft for all this blue screen. And Microsoft said, it's not us, it is not the device driver. So they end up developing tools to help people who write device drivers to check that they are in compliance with the protocol of the operating system.
And that was a problem that was NP complete, so it could be
This
transformed into...
This is even worse than NP complete. It's even worse. We won't even go there. But the point is that this advances in such solver is able us to make advance in many other areas because it is such a fundamental problem. It's just reasoning about 0 and 1. In some sense, it's almost the most, you can think of it in the most fundamental optimization problem. Just zeros and 1. What can be simpler than reasoning about zeros and 1s? Right?
Where else does it occur?
Now, it is used, I know that this is a software for software developers, but you can imagine how useful this would be when people design computer circuits, which are really about zeros and 1s. And in fact, people use it very heavily. I mean, companies such as Intel and other companies have a whole bunch of tools to reason about. For example, here is a circuit, and I've optimized it now using various tools. Are these two circuits equivalent? Do I fully trust my tool? Maybe I should have another sanity check to reason the two tools, the two circuits are equivalent. I'm asking, is there an input where the two circuits will give different results? This is exactly SAT. This is another instance of SAT. So they are now able to reason about much bigger instances as before. And again, because SAT is becoming now kind of a fundamental problem. Whenever you're dealing with a discrete space, you say, I can reduce it to SAT. The same way that many logistical problems are reduced to linear programming. Now people are saying it's discrete. If it's discrete, I can reduce it to SAT.
How would you reduce it?
I need to, for example, I'm doing a register allocation. So inside my compiler, when I go to the final code from the intermediate code to the low level code, I need to do register allocation. Register allocation has been known for a while to be equivalent to some kind of a graph coloring problem. In graph coloring, we're given a graph, and the question is how many colors. You think of it as a map, so we don't want to have neighboring countries having the same color. So the question there is how many colors do you need to color the graph, to color every node, so not two nodes of the same color are connected by an edge. So in this case, the edges represent dependency between variables, and you have to make sure that variables that have dependency, they have to be in memory at the same time, are assigned to different registers. And so people have realized that register allocations required solving graph coloring problem, and which was also an NP-complete problem. So they come up with all kind of heuristics. But now the answer is, it could very well be that inside the compiler, we're going to have a SAT solver that will solve this more efficiently.
While compiling?
While compiling. Because if it's fast enough, maybe not your every compiler, but at least you're optimizing compiler where you're willing to let it run a bit longer. Inside the compiler will call a SAT solver. It will reduce graph coloring to Boolean satisfiability, because after all, even if we have more than two colors, we can always reduce everything to bits. We know that everything finite can be reduced to bits, and Boolean satisfiability is reasoning about bits. And we know that in our field, at the end, there is the bit, the whole bit, and nothing but the bit. Okay? So many problems can be reduced to satisfiability. So we are now in position to start exploring. Not all of this has been done, but now watching the success we've had over the past 25 years, part of my goal here to promote this is to tell the attendees here at ICSI, there is this wonderful tool now. Go explore, see what you can do with it.
Yeah, where do you think SAT solver can be explored where it's not currently? What are some of the, where should we go?
I mean, I go here as I'm here, and I go and I look at some talk, and for example, people talk about combinatorial test generation. And it really talks about what happens if you have, for example, software product line, and there are many possible configurations, and you want to generate data that will cover all these different configurations. And again, a way to do this, you encode all these constraints as Boolean constraints, Everything you reduce. Even we're talking about that maybe a certain option can have, let's say, 8 values. Say, okay, 8 values. This is 3 bits. So I can code 8 values by 3 bits, and I can write all the condition, all the dependencies. I can write all of them at the end as Boolean formulas. And therefore now I can give it to a SAT solver and ask for, is there a solution? Or give me different solutions to cover the different configurations. So now it's up to our imagination. There is this wonderful tool, and it basically can handle it can solve large Boolean constraints. And that means that many problems that we thought were beyond our reach, and we came up with all kind of approximate solution and find a way around it. Now we can say, you know what, let's go for the whole thing. Let's try to solve this problem. Now, there's no guarantee. I said NP complete still does not mean easy, but it means it's hard in the worst case. And worst case is very pessimistic. It just could be that, once in a while we're going to get stuck. But this is life. We don't get everything we want in life. If we get 99%, it's still pretty good. And so I think we have an opportunity now for this tool that exists, and the tools are getting better every year. They are all available. They're available as open source, so people can go and can adapt to their own application. And I think what we need now is for people kind of to move to the next level, which is just, think of what happened, for example, when people discover electricity. The beginning was just moving legs of frogs, right? But then think of what explosion came out when people realized, I can use electricity and for all kind of ideas that nobody would have thought before, right? I can have electric car, a can opener, it's just, people come up with, imagination, or what can I electrify? This is become the electrification of our economy. What
so
else
we need
can electrify?
the satisfaction,
the certification of computer science. What else can we do with it?
Yeah, because the applications you describe are really broad, from test generation to compilers. It's sort of the entire spectrum of programming.
Every place you need to do, you have kind of this combinatorial reasoning. It's reducible to SAT. Remember, SAT is NP complete. So we know that every problem that is in NP, can be checked efficiently, can be in principle reduced to SAT. Now, it doesn't always mean that the reduction to SAT is necessarily a good way of solving the problem. But it's a good first attempt. You should always try that. In particular, because let's suppose that you're trying to solve a range allocation, and you can say, well, but my problem is special. And so I can use special heuristic for my problem because I know this is graph coloring and I know other stuff. I said, yes, you can, but there are hundreds of people who every year are making SAT solvers better. Do you think you can compete with these people? This is a little bit, there used to be a phrase, it was called COTS always win. And COTS stood for commodity off the shelf. And people try to use all kind of specialized architecture for this and for that. And all of this effort have essentially failed because the commodity processors were getting every year better and better and better. So at the end people said your best attempt is just let Intel do its thing. Let's Intel and AMD and whatever do its thing. Just use commodity processors. So SAT solvers are continuing to improve. And therefore at this point it's a very good first strategy is, first of all, let me try to reduce it to SAT. Let it give me an appropriate solution. Because start to develop my own heuristic and my own solvers, this is much harder work than just finding a way to reduce it to SAT.
Yeah, and then you can say you can benefit from all the advancements that have been made, but also that will be made.
That will be made. They are
better.
continuing to improve. Every year they're getting better and better and better. So the same way that you can say, well, this problem is too hard, but next year Intel will come up with a new processor and now I will be able to do it. Now you can say the same thing, well, this is still not good enough. I'm going to another year. The SAT solver will get better in a year and maybe then it will be good enough.
And also, of course, it works double because the SAT solvers get better, but also the machines get better. So the same solver on new hardware will also still improve.
Better, absolutely.
So there's lots of opportunities still to apply this problem that is so old and has been bothering all of us for so long.
I think this is a really very exciting time because again, a problem that we thought was very hard turned out to be not so hard in practice. And now we need people to explore and see what you can do with it. The same way, again, that another technology, whenever we have a new technology, it takes lots of people trying different things to see what can you do with this technology.
I think this is a fantastic way to end the show, that there's so much still ahead of us that We live in exciting times.
We live in very exciting times.
Thanks a lot for being on the show. We will make sure that everything is linked to, so the proofs and also some solvers. So if you really want to check it out after the show, then you can totally do that. Thanks a lot, Moshe, for being on the show.
My pleasure.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.